concrete chain complexes and things that we think about. So the first goal is that I need a more explicit description of this object Q of the infinity algebra. Okay. At the end of the day, we want to take A to B chains on all the GLNs. That's the infinity algebra that we have in mind. But the explicit description is a general thing about all infinity algebras. So I'm going to do this in a quite different way from how it's explained in, for example, the paper that I wrote with Sandu and so on, but is a little more elementary. I want to make use of the following construction. If I have my augmented infinity algebra, I can consider the augmentation twice, and I can make the push out. And that's going to be called bar of A. Okay? So it is whatever the universal object you put there, it's an push out in E infinity algebras. So bar A is the push out in okay? Now you should think of this as being something like suspension. If you have a space and you map it to a point and you take the push out, that's going to be the suspension of a space. Okay? Bearing in mind that every time I say push out or something, I mean maybe not a literal push out, but some homotopically correct push out. So I'll call that bar of A. Why is it called bar? I told you to think of an infinity algebra just like a commutative ring. What is push out of commutative rings? It is tensor product. So if these were just commutative rings, this would be computing the relative tensor product of that tensored with that over that. Okay? And here I'll emphasize it, that of course everything is derived. So I mean some sort of derived tensor product. So the thing whose homology groups would be Tor over A. And there's a canonical way to calculate derived tensor products, of course, it's called the bar construction, and that's why the object's called bar. But this is, one model for it, is the simplicial object whose P simplices are the pth tensor power of A. So that's a simplicial object where the face maps are given by, the outer face maps are given by using the augmentation of A, and the inner face maps are given by multiplying two adjacent things in A. It's just the usual bar construction. Okay? And this is why I call it an explicit model, because it's just given by, okay, you start with A and you do some things that we understand, like tensoring, and then at the end of the day you do some geometric realization, which we also understand what that means homologically. So this itself won't be a model for Q, but it's somehow close to it. So taking ordinary fibers in the square, so this is a push out of infinity algebras, but it's also just a commutative square in the category of chain complexes. And I can just take vertical homotopy fibers, and that gives me a map from the augmentation ideal of A, which is by definition the fiber of this, to the fiber of that, which is, if you think about it, is the desuspension of the augmentation ideal of bar A. Because this is the unit, its augmentation goes that way, but the unit splits the augmentation, so. So you get a map like that. And the sort of explicit model for Q of A is then the following. Q of A is equivalent to iterating that countably many times. So it's the colimit as R goes to infinity of the rth desuspension of the rth iterated bar with a bar on top. Okay? And the colimit is formed using these kind of maps. And then the key point is that bar of A is itself an infinity algebra, so you can do the same construction to it.
So that's E infinity in decomposables.
I mean, that's the only kind I've talked about. I haven't talked about any other kind.
No, but yeah, okay, so no E1, right? Yeah.
The E1 ones would be just do it yourself and stop.
Thank you.
And the EK ones would be do it K times. But we're only doing the infinity ones. So I sort of want to explain briefly why this is plausible. Which is the following. So first notice, just in chain complexes, if I do the analogous thing, or maybe in natural numbers graded chain complexes, if I start with x mapping to 0 twice and take the push out, that's the suspension of x. If you like, that's the definition of the suspension. Okay? So that's the push out in chain complexes. So I can apply the free E infinity algebra functor. And then I get a push out in E infinity algebras because the free functors are left adjoint, so it preserves push outs. So this is a push out in algebras E infinity. But that means I've worked out what bar of this object is. Because it was defined to be the push out of this part of the diagram, and that is a push out, so it is the push out. So the lesson is that on free algebras, we've got a formula for bar. You just take the free thing on the suspension of the old generators. So then we can think about what this kind of thing does on a free algebra. Because remember, we know we have a formula for what a free algebra is. So if I take the free algebra on X and do this A overline mapping to the D suspension, how does that look? How do I write it? So A overline is the augmentation ideal, which means I skip the n equals 0 component, which is the unit of the algebra. Just got rid of the unit. And then there's this map to the D suspension of the overline of the bar version. And then here there's a suspension of X, and then I go taking tensor pairs. Okay? And I won't try to do it rigorously, but I'll tell you something that's incredibly plausible, which is n has become k. The k equals 1 component here is just x, and the k is 1 component here is the D suspension of the suspension of x, aka x, and I claim on that component it's just the identity map. Okay, plausible? The k equals 2 component here is x squared, and here is the D suspension of the double suspension of x squared, so it's the suspension of x squared. And you believe me that there's no reasonable map, there's no universal map from x squared to its suspension. Probably believe me. And so what this map must be is just projection to the k equals 1 summand, followed by inclusion of the k equals 1 summand. Okay? I hope it's plausible. I mean, I'm not claiming to approve it. This is ISO on the k equals 1 summand and 0 otherwise. But what happens then if I do the iterated colimit of doing this countably many times? Every component which is not the first one just dies. Because in the colimit they all die in the next term. And then in the next term I create a load more things, but they all die in the next term after that, and so on. So on colimits, we get just x. Only the k equals 1 term survives. And I just want to write x as q of E infinity plus of x. And then what this shows is that this construction, this iterated bar construction, at least on free algebras, does agree with Q. Because they both send a free algebra on x to just x. That is the end of the sketch. The only thing you need to do to turn this into a real argument is come up with some a priori natural transformation between Q and this colimit. Because then you can test its equivalence just on free things, because everything is a colimit of free things. So that's the step I haven't done, but one can do. So let me just say, so if Q of whatever to this colimit over R is a reasonable map of natural transformation of functors, then the above shows it is an equivalence on free algebras, but then it's an equivalence on all algebras just by resolving them by free algebras. Okay, that's what I want to say about that. So this gives something that's closer to, I mean, Q was just described as an adjoint, just as the abstract property it has. This is something closer to a construction, where you take A and you do well-known constructions to it, and maybe you do them infinitely often. But okay.
Oscar?
Yeah.
About your formula for bar of A, the simplicial picture, what does it mean if A is an E infinity algebra?
So in particular, it has a multiplication. Firstly, it has everything has an augmentation. So the outer face maps of this thing are just given by applying the augmentation to the outer copies of A. The inner face maps are given by multiplying two adjacent copies of A using the map A tensor A to A. That's part of the E infinity structure. And that's it. So it's a simplicial object. It's a simplicial chain complex, and then what do? I think about it as a double complex and then totalize.
So it only uses the binary multiplication?
Yes.
Okay.
This formula only uses the binary multiplication. The fact that this is itself an algebra again is completely not obvious, and is not supposed to be true if you only have an associative algebra. If you do the bar construction of an associative algebra, you get a nothing algebra. So somehow the fact that it's in some sense commutative tells you that when you do the bar construction, you still have a commutative multiplication. In ordinary algebra, that's the shuffle product on the bar construction. It's somehow better, from this point of view, to build a thing that's manifestly in the infinity algebra, like it has this formula, than to try to define it by this formula and then show that you can find an infinity algebra structure in it, which you can never do.
You're effectively using the higher multiplications to build the simplicial object.
So
build the coherences that make it into a
very good. Something for the experts. In this talk, I defined the infinity algebras using the Barrett-Eccles operad, and that has a literal map from the associative operad. So my infinity algebras also have a literally associative multiplication. If you do the little cubes thing, then you typically don't have that. Okay, so there's one more bit of abstraction we need to do before we can go into de-abstraction, which is that, so we want to apply this to the infinity algebra of chains on all the GLNs of some field. And that's still quite a complicated object, of course. And there's a trick you can do to work with a very simple object at the expense of working in a slightly more complicated category. And that's what I want to explain here. So consider the functor from this groupoid of vector spaces over F to the natural numbers that's called rank. It just counts the dimension. So that's a symmetric monoidal functor. And that lets us consider any n-graded chain complex as what you might call a g-graded chain complex. Does that mean? That just means functors from this groupoid. So it means we have one chain complex for every natural number, and the nth one comes with an action of gln. And the things that you get this way, they come with the trivial action of glnf, because I've just used this map to which collapses all the morphisms in this category to a point. Now this has a, I'm going to call it upper star. This has a left adjoint called R lower star, which is what's called Kahn extension in category theory. Let me just write down what the formula is. So the left adjoint is, so let's see, I should start with a functor. Call it x. I push it down, and then I want to tell you what object I get. So I should tell you what object I get in a given grading. And the formula is the following. I look at x of n. That has an action of gln f. And I make the OL construction. Okay. If we were working in ordinary category theory, I would just literally tensor with k, but everything I'm doing is like derived, and so you tensor with a free resolution of k.
And this would just be BGLN tensor X? Because
Yes, so this is, you could write this if you like, as chains on glnf. It's like hyperhomology with coefficients in the chain complex xn.
with trivial action.
No, not with trivial action, with whatever action x being a functor in this category.
Oh, sorry, I was looking at the wrong direction. Yes, yes.
But in particular, we can think about the thing that has a trivial action. So consider, call it k underline, it's just the constant functor that is k at every point. So that's something on the right-hand side. We can push it to the left-hand side and ask what it is. And if we do that, and we look at the formula, we see that this is the object that we're trying to study. It's all the chains on the glnfs with k coefficients. Okay. So the point is that this object, it comes by pushing down an object called k underline, which lives in a much more complicated category of representations of the groupoid G. But in that category, it's a relatively simple object. It's just k in every grade. And that trade-off is a good trade-off to make. It's a good trade-off to work with a simple object in a complicated category than a complicated object in a simple category. I want to say that not only is there a chain complex in there, but it's E-infinity algebra in that category. In fact, it's a literally commutative algebra in that category. But what does that mean? Before I can even make sense of that, I should tell you what it means to tensor things together in this category. And this is where the interest arises.
To what extent is there a difference between commutative and E-infinity algebras if your representation of a groupoid where like a symmetric group injects?
I guess then there's not much difference, yes. In the setting I'm talking about, like if you work infinity categorically, you can't even say a difference. I mean, commutative algebra is infinity algebra. There's no...
But classically...
yeah, if you know, that's probably true. If you know the symmetry groups inject into the automorphisms in the category, probably that's more or less the same, yes. So how does tensoring in this category work? This is something called Day convolution. It was given by formula, and I will tell you the formula. So I have two functors. I want to tensor them and tell you what you get when you evaluate at n. Whatever it is, it should be a representation of GLN, because that's what objects in this category are. It should be a chain complex with an action of GLN, and it's given by the following. You sum over decompositions of n of let me write the formula. I evaluate the functor A at the element little a, I evaluate the functor B at the element little b. That has an action of GLA, that has an action of GLB. So the whole thing has an action of GLA times GLB, and I induce it up to GLN. Okay. You can take this literal formula as the definition if you like, and then you can go and check that it is a monoidal structure. Or better, you can define a monoidal structure abstractly and check that this formula describes it. Let's just take the formula as the definition. So with this product, K underline is it's even literally commutative, as Jeremy says, but in particular it's then A infinity. Incidentally, that gives another proof that this object is, because this push forward is lacks symmetric monoidal, so it sends commutative algebras to, or infinity algebras to infinity algebras. So the game is going to be to work in this groupoid graded situation for as long as possible, because in that situation the object we're working with is quite simple. And then as late as possible, use pushing forward to the natural numbers to translate statements into statements about GLN over F. So I promised that things were going to become concrete, and this is where they do so. Everything I've said before section 4, I was working in this category of n-graded things, but literally everything I said can be implemented in g-graded things. And at the level of symbols, nothing changes. So you can do bar, you can talk about infinity algebras, you can do Q, you can do all these things. In particular, I can do bar of this constant functor K underline. That's a G-graded thing. I can evaluate at N. That should be a representation of GLN F. So what is it? So this is the double extension of the reduced K chains of the following simplicial set. The simplicial set that sends P to the set of decompositions of the n-dimensional vector space into P plus 2 summands. Non-zero summands. How is this a simplicial set? It's a simplicial set by the face maps act by adding adjacent summands together. Okay? That's why there's P plus 2 of them, because then there are P plus 1 gaps between them, and there are P plus 1 face maps. And the face maps are given by merging in the gaps between them. So this is just an ordinary simplicial set, and you can think about it using ordinary non-homotopical thoughts. Say again?
Why do they have to be non-zero?
So you can allow them to be 0. In fact, if you want to say simplicial set,
In your definition, it seemed to me like they might be 0.
if you want to say simplicial set, then you have to allow them to be 0 because that's what the degeneracies are. So what I've written down here is like the normalized.
I like this better, but I
Yes,
just
me
want
too.
to
So let's.
it.
All right. So I'm gonna actually prove this. So this you should think of as a semi-simple set. Maybe it only has face maps, not degeneracies. So to prove this, we're just going to literally use the definition. So bar k n was defined to be the geometric realization or the totalization of a simplicial object, which was p goes to, I tensor this object p times, and I use the associativity, and I guess I'm meant to be evaluating at some particular place n. I can do the evaluation on the inside. So I now just need to work out what does the p-fold tensor product of this object k mean when you evaluated n. And we had a formula for the two-fold tensor product, and you can work out what the formula for the p-fold tensor product is. It's the obvious generalization of that. You sum over decompositions into p pieces of, I induce up to GLN. Let me not write the field all the time for sanity. That's the formula. And then I guess I would bar. And what is this? This is just a trivial representation of this group. Right, K itself was just K with a trivial action of GLN1. I've tensored them together with their external action, but it's still the trivial action. And then I induce up. So another way to write exactly the same thing is the sum over the same pieces of the vector space on the cosets.
Do you allow the n's here to be 0 now?
Yes, because here we don't get a choice. We have to just look at the formula and do what the formula says.
Yeah.
So now, the rest of the proof, there's two steps. The most important one is simply to interpret what this is saying in ways that are not overtly about GLN. This set of cosets is exactly the same as the set of decompositions of f to the n into pieces of size n1, n2, up to np. Why? Because GLN acts on the subsets of decompositions transitively, and this is exactly the stabilizer. So this is exactly the same as and if I write it that way, I don't need to sum, because I haven't said what their dimensions are. Here I've written it as a sum over dimensions, and this is just a sum over all decompositions. Here they're allowed to be 0. Okay, that's just literally isomorphic to that. And obviously it has an action of GLN, which is just given by you act on Fn, and that moves these summands around. So there's two differences between this and that. One is that here I'm allowed things to be 0, and the other is that there seem to be the wrong number of them compared to what I set up there. Okay? The second thing is easy to resolve, and is because what do the outer face maps do here? They forget V1 or they forget VP, because that's what the augmentation on K underline does. But if I forget V1 and V1 is not 0, what I get is never a decomposition of Fn. And so the only thing I can sensibly set it to be is 0. And that's what the face maps do. So let me just write that. The face maps are, so D0 forgets V, so did I get this right? Yes, V1. And we get 0 if V1 wasn't 0, because then what's left is not a decomposition. Similarly, D, the last one, dP forgets VP, and again we get 0 if VP is not 0. And the D inner, they add adjacent things just as above.
The very outer one says just because of what the augmentation is in this case.
The augmentation, I didn't make a point of this, but K underline is K in every degree. The unit is K only in degree 0 and 0 otherwise. So the augmentation kills everything of strictly positive rank. Which is, what does it say? So then to get to the statement, to proof as I've said it, you should do two things. One is you should collapse the degenerate simplices. That doesn't change the homotopy type of the chain complex. And the degenerate simplices are just when some VI is 0. You should collapse those, and that's how this VI not 0 shows up. And once you've done that, once you've forced all the VI's to be non-zero, the outer face maps are both just 0. Because V1 is definitely not 0, and so when I forget it, I definitely drop rank. But the two outer face maps being 0 is exactly what the double suspension is. If I take a chain complex, if I take a simplicial object, shift everything up and add a new face map which is 0, that is the simplicial suspension. And I've done it on the left and on the right. I don't know how to write that on the board. So let's just say taking or collapsing degenerate simplices. This is visibly the double suspension of the claimed thing. If you didn't want to do this move, another way of writing down what this is here is it's abstract direct sums with a map to Fn, modulo those that are not isomorphisms. And then when you forget things, if you've made them too small, then you've gone to 0. So this simplicial set, or semi-simplicial set, may be familiar to some people. This is a version of the Tietz building, except that I haven't taken flags of subspaces of Fn. I've taken flags with a complementary flag. So I've taken decompositions. Make some definitions. One T tilde of Fn is this object. So this the thing P goes to decompositions V0 to Vp of Fn, Vp plus 1, sorry. 2 P of Fn, that's the simplicial object that sends P to flags of length P plus 1.
Is the first one also an equal sign?
Is the first one, sorry?
Are you equal to 0?
No.
Okay.
No. So this we saw yesterday in Jenny's talk. This is just another way of writing the Tietz build. And it was also in that talk. Sorry?
Oh, it might be off.
No, I think it's, yeah, it's what, sorry.
Yeah, I'll come back to that. And there's a map between them.
This is the double suspension of the Tietz building, right?
No.
No?
Then P plus 1 should be P.
Here's an equal sign is the last thing. That's fine.
Okay, I see. Oh, so this is actually the Tietz building.
So there's a map between them, If I have a decomposition, then I get a flag just by taking the partial sums of the decomposition. By taking partial sums. I.e. setting Wi to be the sum of the first I v's, or the first I plus 1 v. So, as Jenny also said yesterday, the Solomon-Tietz theorem says that T of Fn is a wedge of n minus 2 spheres. And the exact same thing for T tilde was proved by Charney. It's a different wedge of spheres, but it's also a wedge of Sn minus 2 spheres. And the Steinberg module was defined as the unique reduced homology group of this. And similarly, the thing that we call the split Steinberg module, or the E1 Steinberg module, is the unique reduced homology group of the split version. So if you say it that way, then what does the theorem here plus Charney's theorem tell us? It tells us what the homology of this object is completely. For every n, it has a single homology group, which is in degree n, because it's the double suspension of something that's a wedge of n minus 2 spheres. So when you suspend it twice, it's a wedge of n spheres. And in that degree, it's this split Steinberg module. So HD of this bar k n is 0 if d is not n, and it's this split Steinberg module if d is n. So, okay, the split Steinberg module is a name for something, but we don't know anything about it. But it's the only homology group of this bar construction. And so one thing we can do, given that, is we can apply this R lower star, push it forward to the natural numbers. And if we do that, we will discover that if I do bar of the thing I'm really interested in, chains on the GLNFs, this is given by, one way to write it is HD minus n of GLNF with coefficients in this object. Because pushing down from G graded things to natural numbers graded things is exactly taking group homology with respect to the GLNF. And if I write it that way, one obvious point is that this is 0 for d less than n, obviously, if I write it like that. Okay? That's because upstairs it was 0 for d less than n, certainly. And by taking a homotopy quotient, you can't make new homology group at O where you have homology. You can make new stuff above. That's called group homology. You can make new stuff above. So, something you can check using the literal formula for the bar construction is that if I have a infinity algebra that has a vanishing line like this, and I take bar of it, it has a vanishing line of the same form, but you get a +1 here. So in other words, taking bar increases connectivities by 1. So taking bar and desuspending increases connectivities by nothing, but does not decrease connectivity. That's the key point. So desuspension bar of whatever blank does not, this is not an implication, this is an observation, does not decrease connectivity. So if the one-fold bar construction has this kind of vanishing, then this iterated infinite-fold one still has a kind of vanishing. And what that says is that the E-infinity homology of this object chains on GLNFs vanishes for d less than n minus 1. There's a minus 1 because to get started I have to desuspend this one. And then this becomes minus 1. But after that, further iterations don't drop connectivity. Let me remind you of what this means. It means that if you draw this picture that I've drawn 1,000,000 times in my life, so much so that my partner can reproduce it from memory, even though she has no idea what it means. It means that the E-infinity homology is supported on and above this line of slope 1 going through 1, 0. In other words, you can build this E-infinity algebra only using E-infinity cells whose bi-degrees, D and N, are in this region. In other words, you never need to attach a very small dimensional E-infinity cell in very large rank. Okay? That's what the consequence is. So I won't do it because I'll do something better in a minute, but from that picture, it's a trivial consequence to prove that GLNFs have slope 1/2 homological stability. And that's because when you start building them, you attach a cell here, which was this thing I called sigma, and once you do that, you've just made the homology of the symmetric groups. The free E-infinity algebra 1 generator is the homology of the symmetric groups, and observationally, we know what those are, and they have homological stability of slope 1/2. And the next thing you need to add has slope at least 1/2, because there's no cells down here. And the little exercise you can do is if you have something that has slope 1/2 stability and you attach a new E-infinity cell of slope bigger than 1/2, you'll change the homology, but you won't change the fact that it has slope 1/2 stability. So the fact that the symmetric groups have it means that gets inherited by the general linear groups. In a spirit of honesty, let me say here, I've been saying F is a field, and everything is safe if it's a field, it's safe if it's a PID. This is true if F is a Dedekind domain. Then some other things I've said you should be a bit careful about, like you can't just count the rank n anymore, maybe, or you shouldn't. There's not a single module of rank n. So for Dedekind domains you should be a bit more careful, but Charney's theorem is still true, and that's the main driving force behind the thing. So I need to give a summary. I want to do this in a bit more detail, but I think I don't have time, of some things that Sander, Son, and I proved that go beyond this, which are specific to infinite fields. And I think I'm just going to have to assert what happens. So we have a paper called E-infinity cells and general linear groups over infinite fields, and it's in that paper. Which, let me just say the conclusion. If F is an infinite field, then in fact, something much better is true. In fact, this is 0 for d less than 2 times n minus 1. In other words, if I could recycle that picture, there's a much steeper line of slope 2 below which you don't need any cells, if it's an infinite field. More generally, if it's a semi-local ring, all of whose residue fields are infinite. So this I won't go into because the core thing behind this is very close to what I think Jeremy will talk about, which is this area of Rogners conjecture and things like that, which has to do with things being approximately twice as connected as you thought they were supposed to be. Let me say in words a little bit what goes into it. If I tried to reproduce the argument that this was the proof of, for bar of k, how would the description of that go? That would be not decompositions, not direct sum decompositions of the module into linearly ordered factors, but direct sums of f to the n into a grid of factors. It's the twofold bar construction. So you have to study bisimplicial object of decompositions into p+1 columns and q+1 rows of your module. I guess proper decompositions. So that's a bisimplicial object. It seems quite different. It turns out that at the level of taking homology, it's sort of indistinguishable from two copies of the TITS building smashed together and suspended 4 times. And that means it has twice as good connectivity as the TITS building does, because when you smash things together, their connectivities add. That argument, you can't say, well, maybe if I do it 3 times, then I smash together 3 TITS buildings and it becomes 3 times as good connected. It turns out that there's a crucial step that only works if you do it twice, which is that inclusion-exclusion, the dimensions of vector spaces, is true for 2 vector spaces, but is not true for more than 2 vector spaces. So that's what goes into it, and it gives this, I should emphasize it, the difference is this crucial factor of 2, which means that there's many more zeros in the picture. That's the upshot. We also work out what happens along this line. So what is it? The line would be 2 times n minus 1 of the same thing. And it's a quite surprising formula. If you know where it comes from, it's not so surprising. But if you don't know where it comes from, it's very surprising. So this is z if n is 1. It's z mod p if n is a prime power, a power of the prime p. And it's 0 otherwise. I've written z, of course. I was working with a field k of coefficients, so you should just write k and k mod p. It is true of integers. The upshot for what I want to talk about next time will be that even on this line, if we work rationally, all of these vanish. So we get a little more vanishing than below the line. We also get vanishing on the line, apart from in grading 1, where there's this class sigma which has to be there, because we have to make the BGLs be non-empty spaces. So you have to attach at least a 0. So. Let me point out something, one final thing, which is not actually written anywhere, but I think it's interesting to this audience. And I can explain to you, if you ask me, how it goes. So this is a corollary of that theorem. And this has been discovered independently by Soren, Sander, and me. 3 times. And it says the following, let me get it right. HD, in the same setting, so infinite field, of GLNF with coefficients in the ordinary Steinberg of f to the n is 0 for d less than n minus 1. I think that's right, yes.
Integrally?
Yes.
Okay.
Yes. The way I've said it here is over field always, but yes, integrally.
For infinite fields or for?
Yes. So as above, so f, infinite field. Maybe also for this semi-local, but let's say infinite fields. Okay, let me stop there for now.
Questions, Peter?
Does this also imply this? I mean, I guess infinite fields, this Steinberg and split Steinberg gives the same thing there, right?
That's part of the argument here.
Oh, that's the argument. And then if you invert the correct primes, you get slope 2 homological stability then?
No. So the whole next talk is going to be about what you get out of it.
Okay, great. Now
You get things to do with Milnor K-theory and this theorem of Sustin-Nestorenko and stuff like that.
Any other questions?
Where do you use that the field is infinite?
Didn't you guys also prove it for finite fields, that corollary?
Oh yes, but that's somehow cheaper. You use, I don't remember. I mean, I'm probably use it crucially. Yes, right. Yes, very good. We use often. So, for example, this happens to be the same as the E1 version, which is what we actually prove. And the infinite field is used partly to say that those are the same. So the modules are not the same, but their homologies are the same. Why is that? Because when you act on the Tietz building by GLN, the stabilizers, when you act on the ordinary Tietz building, are block upper triangular matrices. And the stabilizers, when you act on the split Tietz building, are block diagonal matrices. And those are different groups. But they have, when the field's infinite, they have the same group homology. I mean, the canonical inclusion or projection is a homology isomorphism. So that's theorem of Suslin and Nestorenko, I suppose. Maybe just of Suslin. And that lets you interchange, at the level of taking homology of things, it lets you interchange direct sum decompositions and flags at will. You can go back and forth. And that's also what's involved in proving this slope 2 thing. You don't really get to Tietz buildings, you go from the direct sum version to a flag version. The flag version is the smash product of the two one-dimensional flag versions. And then at the level of homology, the flag versions are the same as the direct sum versions again. But the actual modules are not the same, only the homologies are the same. So the basic example you want is to convince yourself that the inclusion matrices like that is is an integral homology isomorphism if you work over an infinite field. Or the other way, so that's a key way.
Okay, we'll continue at 10.